Welcome. This video is going to take a look at metallic bonds and specifically look at how it's related to, or similar to, I should say, an ionic bond. Metals are unique for a lot of reasons, and one of those reasons is because metals can only bond to themselves. And I mean not just to other metals, but to themselves. Gold only bonds to gold, silver only bonds to silver. Now they can bond to nonmetals and form ionic compounds, as we've seen, but metals don't bond to other metals, at least not chemically. They simply mix with each other. So metals don't transfer or share electrons with themselves because they both need to lose electrons. So sharing doesn't really work and transferring doesn't really work. So instead, they form a lattice, and that should sound familiar because that's what ionic compounds do. But now you have 8 or 12 metal atoms surrounding every single metal atom. So one atom has 8 to 12 metal atoms surrounding it. And with metal atoms, surrounding each other that tightly and that crowded, the outer energy levels are going to overlap. So then the valence electrons end up getting pooled together, so each individual nuclei behaves like it has 8 electrons, even though it only started with maybe 1 or 2 valence electrons. So here's a graphic to try and show you the difference between an ionic bond and a metallic bond. So with an ionic bond, remember, you have a crystal lattice and you have alternating cations and anions. And that makes ionic compounds rigid, hard, high melting points, high boiling points. They're brittle when they're hit, but they're poor conductors as solid. They have to be in a solution or dissolve before they're free to move and become good conductors, or what we call electrolytes. Metallic bonds, on the other hand, form this lattice, but now the positive nuclei line up and they act like the metal cation, and they're surrounded by this, what we call a sea of electrons. So they're also rigid and hard, and they have fairly high melting points and boiling points, but instead of being brittle like ionic bonds, they're actually malleable and ductile. You can flatten them out into sheets or stretch them out into wires, and they're also good conductors as both solids and liquids. So if you look again, the difference is ionic bonds have alternating positive ions and negative ions, whereas metallic bonds have the positive nuclei are lined up nice and rigid or neat, but those electrons move quite freely and surround or pool around. So it's actually called the electron sea model because the valence electrons form a sea of electrons around the positive nuclei. And because the electrons are free to move, they're given the name delocalized electrons. And I know that sounds kind of funny, but local means you stay in one area. Delocalized means they're free to go wherever. The positive nuclei are also called the metal cations, even though they're not really cations because they haven't gained or lost anything, but they do have a positive charge like cations. And then the freely moving electrons act like the anions. And so a metallic bond forms because the positive nuclei attract the delocalized electrons that are pooled around them. So metallic properties, as I mentioned on that graphic earlier, metals tend to have moderately high melting points, not quite as high as ionic compounds, and it does vary because there are a lot of metals. So mercury's boiling point is, or melting point is minus 38.9, so it's actually a liquid at room temperature. But you look at tungsten with a melting point of 3,422, that's a lot of heat to get tungsten to melt. They also tend to have moderately high boiling points. And again, instead of being brittle like ionic compounds, they're malleable and they're ductile. They're also what we call durable. Metals don't wear down easily, and that's why we like them for so many things that we use in our day-to-day lives. They're also good conductors of both heat and electricity, and we certainly use that a lot in our day-to-day lives. And for jewelry and some other things, it's very nice that they have what we call luster, which means they're shiny. They reflect a lot of light. They can absorb and reflect it back. So the big question is, why do metals have these properties when ionic compounds don't? If they're bonding in similar ways, what gives metals that flexibility to be able to flatten them out or stretch them into wires? How come their ions can move, or their electrons and nuclei can move to conduct electricity, and ionic compounds can't? Well, it's really all about the delocalized electrons. The d orbital electrons in transition metals make this even more pronounced because you can have even more delocalized electrons. But if you look at the graphic here, and I'm going to try and blow this up a little bit. So with an ionic compound, because the cation and anions have to alternate, and because what holds them together is the attraction between these opposite charges, if you look at the graphic here, if you hit an ionic compound with a hammer, you're going to disrupt that rigid, repeating pattern. And when you disrupt that and you end up with two cations near each other and two anions each other, as you can see in the third picture over to the right, that's going to repel or break the ionic compound apart. And that's what gives ionic compounds their brittleness. But with a metal, and it's hard to see here, but the blue represents the sea of electrons. So think of lots of little negative charges in here. Because the only thing that's lined up neatly and keeping a pattern is the positive nuclei, but the electrons in here, if I can get my pen, the electrons in here are free to move around. So if I just draw some electrons in there, when you hit this with a hammer, you're not going to disrupt that pattern because it's all positive nuclei that are lined up, and the electrons will easily move and make room for those cations, those positive nuclei, to get pushed through. So that's why metals have such different properties. The last thing to discuss is something called metal alloys. Earlier when I said metals do not chemically combine with other metals, that's true, but they do easily mix together. And that's where we get a lot of the metals we use in our day-to-day lives. So a mixture of two or more elements that has metallic properties is called an alloy. It's usually two or more metals being mixed, but occasionally you can mix a metal with a non-metal and still get metallic properties. And an example of that is carbon is often used. You maybe have heard of carbon steel. And the reason it's done is to get the good qualities of both elements. For example, if you want a lightweight but strong metal, you could find a metal that's lightweight but not particularly strong and combine it with a heavier metal that is strong and hopefully form an alloy that's both lightweight and strong. And there's two kinds of alloys that are easy to form. One is called substitution and the other is called interstitial. And we'll look at each here. Substitution alloys are just what they sound like. It occurs when atoms of the different elements are similar in size and atoms of one element are substituted for or replace atoms of the other element. So, for example, copper atoms replace silver atoms to form sterling silver. And if you've ever seen sterling silver, it looks like pure silver. It still has that silver look, but there's actually copper atoms in there as well, and that brings down the cost of sterling silver as opposed to 100% pure silver. Other common substitution alloys that you maybe have heard of are brass, pewter, and 10-karat gold. And in fact, I'm guessing some of you maybe have done a lab where you take a penny and you initially plate some zinc onto it, and then you later heat your silver or zinc penny up and it turns to gold. That would be a substitution alloy where the zinc and copper atoms are replacing each other, and when they get mixed together, you end up with this pretty yellow or goldish color that we refer to as brass. Interstitial alloys are used a lot in industry. This occurs when one atom is much bigger than the other atom, and then the smaller atom is used to fill in the spaces or the interstices. Think of interstices as like being intersections of the bigger atom. So think of it like pouring sand into a bucket of gravel. If you had a bucket of gravel completely full and there was no room for any more gravel in there, you could add a lot of sand because that sand would go down and fill in the spaces between those big chunks of gravel. And this is done, as I said, in industry often to strengthen things. Common example is carbon is added to iron to form what we call carbon steel because it makes it harder, stronger, and less ductile. Look at a couple of quick graphics here. Up above, the first one, the substitution alloy, this was what was going on when you made gold pennies. You had the silver coating on the penny, the zinc, and as you heated it up, some of the copper atoms, so if these are the copper atoms here, some of the copper atoms gained enough energy to move to the surface and bump a few of the zinc atoms down below. And so if these were all zinc, this would form the alloy brass. Whereas with the interstitial alloy, if these bigger atoms are all not carbon, if these are all iron atoms, okay, bigger, larger iron, if you look, it's number 26, so it's getting up there in size. And then in between, if you put carbon atoms in, if you think about trying to, let me get blue there instead so you can see this. If you think about trying to bend this metal, you can see by putting the carbon in between that it may make it harder to separate that. Let me just get the correct symbol here, just carbon, not copper. But that's an interstitial alloy.